Hey, we have a couple of loose ends to tie up. The first is the derivative of the natural log of the absolute value of x. So you'll certainly recall that we recently determined that the derivative of the natural log of x is 1 over x. But the natural log of x is sort of a very restricted function. It's only defined for positive real numbers. On the other hand, the natural log of the absolute value of x, a much nicer function defined for every real number except 0. And what is the natural log of the absolute value of x? Well, we can define it this way. If x is a positive number, then it's just the natural log of x. If x is a negative number, then it's the natural log of negative x. In other words, imagine x is negative 7, then the absolute value of negative 7 is 7, or negative 7. And breaking it into 2 as a piecewise function like this lets us take the derivative of each piece. Certainly if x is greater than 0, then we already know the answer. The derivative of the natural log of x is just 1 over x. On the other hand, if x is less than 0, then the derivative of the natural log of negative x is a chain rule problem. We have to treat the negative x as if it were a variable. And that gives us 1 over negative x. And now we have to multiply by the derivative of the function that we just treated like a variable. And the derivative of negative x is negative 1. And when you multiply 1 over negative x by negative 1, you just get 1 over x. And what did we just find? We just found that the derivative of the natural log of the absolute value of x is equal to 1 over x, just like the derivative of the natural log of x was. And yet the natural log of absolute value of x has a much larger domain, so this is in some ways a better function. It won't matter much early in the semester. Later in the semester, we're going to start doing things backwards, where instead of giving you a function and you taking the derivative, I will be giving you a function and saying, what was it the derivative of? And then this concept will come up much more frequently. So tuck this into the back of your mind for later use. Okay, for the second of the loose ends that we need to tie up, we first have to develop a new technique known as logarithmic differentiation. Here it comes. Consider yet again the function y equals 1 over x. Well, if y equals 1 over x, then it is certainly the case that the natural log of y is equal to the natural log of 1 over x. And then we can take advantage of properties of logarithms to rewrite that as natural log of 1 minus the natural log of x. And since the natural log of 1 is 0, this simplifies to natural log of y equals negative natural log of x. I now want to do implicit differentiation, meaning take the derivative of both sides of the equation with respect to the variable x. And on the left, you have to use the chain rule because y is a function, not the variable, and you get 1 over y times the derivative of that function, dy dx. And on the right, you can just pull the negative outside of the derivative, and you get that the derivative of the negative natural log of x is negative 1 over x. And then as we've seen before, after you do the algebra, you get that dy dx is negative y over x. And since y is 1 over x, this simplifies to negative 1 over x squared, just like it has every other time that we have taken the derivative of 1 over x. So the interesting thing here was not finding the derivative of 1 over x. It was developing this new technique. This technique is called logarithmic differentiation. You start by taking the log of both sides, and then you go from there. And why do we care? We care because of this function, y equals x to the n, which to date, we only know how to take the derivative of this function where n is a natural number, 1, 2, 3, 4, etc. And logarithmic differentiation is going to let us improve that situation. So we start by taking the natural log of both sides. And then on the right, we can use the properties of logarithms to rewrite the natural log of x to the n as n times the natural log of x. And then we take the derivative of both sides with respect to x. And as before, on the left, we get 1 over y times dy dx by the chain rule. And on the right, n is just a number, so the derivative of n times the natural log of x is n times 1 over x. Multiplying both sides by y gives us that dy dx is n over x times y. And since y is equal to x to the n, after you simplify, you get that the derivative is equal to n times x to the n minus 1. Just like we knew it was when n was a natural number. But nowhere in here did we use the idea that n was a natural number. We did when we did this originally for natural numbers using Pascal's triangle, but now n can be any real number. And you say to yourself, why is that so interesting? Well, good question. Let's take a look and see. It's interesting because we can now answer questions like, what is the derivative of the square root of x? We just have to remember that the square root of x is x to the 1/2 in terms of properties of exponents, and now we can simply apply the rule. And the rule tells us that the derivative of x to the 1/2 is 1/2 times x to the 1/2 minus 1, which is negative 1/2. And if you wanted to, you can rewrite that as 1 over 2 square roots of x, because x to the negative 1/2 is 1 over the square root of x. Let's do another. I promised we would do this one over and over again, many different ways. So here comes yet another. The derivative of 1 over x is just the derivative of x to the negative 1, because x to the negative 1 is 1 over x. Now we can apply our new rule and see that the derivative is negative x to the negative 2. And x to the negative 2 is 1 over x squared, so just like it always is, the derivative of 1 over x is negative 1 over x squared. Okay, you try these. Find the derivatives of the functions f of x equals 1 over x to the 4th, and g of x is the square root of x squared plus 1. So take a few minutes, pause the video, and when you're ready, start it back up, and we'll see how you did. The trick for this first one is, before you do any calculus, to rewrite 1 over x to the 4th as x to the negative 4. That's just algebra, basic properties of exponents. And once you've done that, taking the derivative is trivial. It's negative 4x to the negative 5. Or, if you prefer, negative 4 over x to the 5th. And I say if you prefer because it really is up to you. These are both the same thing. X to the negative 5, 1 over x to the 5th. Those are the same thing. So either way, just as good for me, they're the same. As far as the second function g is concerned, same idea. Before you do any calculus, you have to rewrite square root of x squared plus 1 as x squared plus 1 all to the 1/2 power by the properties of exponents. And now, to take the derivative, this is a chain rule problem. We have a function to the 1/2 power. So you treat that function as if it were a variable, which gives us 1/2 times that function to the negative 1/2 power. And then you have to finish by multiplying by the derivative of the function that you just treated like a variable. And the derivative of x squared plus 1 is 2x. You would certainly never leave it like that because you have 1/2 times something times 2 times something, and so you have to simplify. 1/2 times 2 is 1. And so you could rewrite this as x times x squared plus 1 all to the negative 1/2. It's a little bit nicer with the x out in front. Or, if you prefer, x over the square root of x squared plus 1. So hopefully it's easy for you to see why those are the same. Either answer is fine. Okay, just to remind you about some basic properties of exponents that you will certainly need for your homework. 1 over x to the n, same thing as x to the negative n. We just saw that a couple of times. The nth root of x is x to the 1 over n, so the 7th root of x is x to the 1/7. And then finally, the nth root of x to the m, which is the same thing as the nth root of x, all to the m, is just x to the m over n. And on Blackboard, you'll find a document with the properties of exponents that explains where these come from, along with a bunch of other properties of exponents. And if they're rusty for you, you should take a look at that and make sure that it's all clear in your head so that you're all set to do the calculus. You need to be able to do the algebra first before you can do the calculus. Okay, those were the loose ends I wanted to tie up today. The second one of great importance, you don't really need the technique of logarithmic differentiation. We needed it to develop that second rule. But after that, I don't need you to be able to do it, although it certainly can't hurt and it's not hard. There is, of course, a homework on this stuff. So take a look at that, have some fun with it, and I look forward to seeing you in class. Bye.